All right. So, a couple things off the top. So, I will be putting up what looks like a homework. It is not. It's just using that Connect platform. And it's just going to be some additional practice problems with hypothesis testing problems. So it's like you've got the 2 practice exams that I put up there last week. Those should be under the exam 2 practice material folder under the files tab. It also has the formula sheet that you'll have in that folder for the upcoming exam. But on top of those practice exams, if you want some additional hypothesis testing stuff, that like what looks like an assignment will be up there. I might have to assign, I think I have to assign like 1 point to it so it'll look like it's worth something. It's not worth any points. It's just up there for practice. Okay. I will also get some videos later this week of me working through some of those practice problems as we get closer to the exam. So you'll kind of, we'll have some review on Monday, but we'll also kind of have some additional videos of stuff that, we won't have time to cover in class. Those will be up there on that YouTube playlist. So you might see those kind of start popping up, similar to the last exam where I kind of identify what questions I'm covering in each one of those videos. Okay. After today, that Excel assignment, I think I put in the announcement last week that I was updating the due date and I mentioned in class. I apparently didn't hit save when I changed it. So I went in earlier today and it should now look like it's due Friday at the end of the day this week. So have the entire week to work on it. I would suggest working on it early in the week because I don't have office hours Friday. So if you wait to do it Friday, I'm probably not going to be able to help you as much with it. So take a look at it early, start to stop by. If you have questions kind of earlier in the week, that way we're not kind of cramming that all towards the end of the week with last minute questions. I'll also get an announcement up on Canvas today. My office hours today, I had a meeting that popped up, so I'm not going to be able to be there. So instead of 2 to 4 today, I'll be in my office tomorrow from 10 to 2, right? So 10 to 2 office hours tomorrow, as well as the usual 3:30 to 4:30 office hour tomorrow as well, okay? So make sure I'm not going to take any time away if you wanted to stop by, all right? Any other questions from me before we kind of jump into material here today? Okay, so that should be all the, I think, housekeeping stuff. If I remember something else, I'll mention it, but I think that was everything I wanted to kind of get out of the way before we jumped into material. So we left off thinking about, we're building confidence intervals, and we looked at examples where we're building a confidence interval where the true population mean was, but we somehow had this population variance that didn't really make a lot of sense. So instead of going to work on examples where we only have a sample variance, we don't have some known population variance. We said, how's that going to change things? Really, all it changes is that instead of the standard normal distribution or a Z value, we're now going to have to use a student T distribution or use a T value. Now it still represents, I want to move a certain number of standard deviations away, but my data is going to be slightly distributed slightly differently than when we had a known population variance. And we kind of talked about that last class. So the steps are really look very similar to what we were doing before, just we're using that student T distribution. And we can use this, calculate our intermediate step, which was the standard deviation of our sample means. Instead of a known population variance, we can use our best estimate, which is the sample variance that we can calculate. Okay. So we'll work through a couple problems by hand, and then I'll show you what this looks like in Excel, and then I'll introduce that next topic, which I said we would start today, which is hypothesis testing. Okay. So this first example, not a lot of context to it, but at least lets us see how these steps look and put some actual values in things. So we've got a sample of 36. I'm just going to write these down so when we go to the dot cam, I don't forget the values. We have a sample variance and a sample mean that we calculated from our sample of 324 and 9. If we then wanted to build a confidence interval where it corresponds to an alpha of 0.01, what level of confidence am I going to be looking for there? Yeah, 99%, right? Alpha is the decimal form of what's outside the interval. So if we have a 99% interval, 1% is outside, in decimal form, 0.01. Okay. So we know that our confidence interval equation is going to look something like this. I'm going to write this a little bit different so I can make a point here as well. And that standard deviation of my sample means is the original sample variance over my sample size, taking this square root. Yeah, so I'll explain that here. So the reason why I'm putting this in parentheses is because I don't want to make anyone confused. So in my earlier section at one point, I didn't include this, and they're like, so I'm multiplying. This is one value. I'm just using subscripts to denote this is the t-value that gives me alpha over 2 on each side of the interval, and that corresponds to whatever my degrees of freedom is. Okay? So these subscripts are just identifying this is the t-value that goes with this area, alpha over 2, for this degrees of freedom. Because we said it's not one student t-distribution. There's a different student t-distribution for every degrees of freedom. And here, it's pretty simple for the examples we'll be looking at. Our degrees of freedom is simply our sample size minus 1. For other types of analysis that we'll do down the road, or stuff we won't even do in this class, it can be something other than the sample size minus 1. But, you know, so we're just kind of getting familiar with this term of degrees of freedom. At least it's easy starting out. Just our sample size minus 1. Okay. Any questions before we kind of continue with this? So we've really got everything we need. I mean, I could already do this intermediate calculation. So the square root of what? 324 over my sample size of 36. I think this works out to be 3. We've got our sample mean, so I could plug that in here. My standard deviation of my sample means I just calculated, which was 3. The only thing left I need to do is look up that t-value. Okay. So what is that t-value? Well, it's normal. It's a normal distribution. It's not standard normally distributed, but they're normally distributed. And I'm trying to find the number of standard deviations away I need to go to the left and the right that gives me that desired alpha in the tail, or 0.01 in the tail. Well, I've got 2 sides of my confidence interval. So that means that half of alpha is on each side. So 0.01 over 2, or 0.005 is the area kind of in each of these tails, or on each side of my interval. Right. The other thing I need when I'm dealing with a student t distribution is, well, which one am I using? What's my degrees of freedom? Well, here, my sample size was 36 minus 1, so my degrees of freedom is 35. Right. So now when I go to the table to look up this number of standard deviations away I need to go, or the t-value that I want, I not only need the area on each side of the interval, alpha over 2, I also need my degrees of freedom. So I've got 35 is my degrees of freedom, 0.005 is that area I want in the tail. Leave this open down here. Well, actually, I got to raise this up a little bit so I can open up these t-tables, right? So we've just taken our first look at them last week. But the one thing that was a little bit different with the t-table compared to the standard normal table was that it's always looking at the right side of the distribution. That way, we're always dealing with the positive values, right? So it makes it a little bit easier for us. So I want the area of 0.005 on each side. So in that upper tail and in that right tail, or lower left tail. So 0.005. And now I just scroll down to my degrees of freedom, which was 35. Looks like it's on the second page of the student t distribution table. So degrees of freedom of 35, area of 0.005, 2.724. So I just plug in that value for I found the t value. Now it's a pretty simple equation to get entered into my calculator there. Okay. Any questions about how I use the table? Kind of any one of the steps that we had here, or anything before we go to an example with a little bit more context? Okay. So if I actually enter this into my calculator, right, we identified everything that we were given. We found that t-value. I can calculate the standard deviation of my sample means as the intermediate calculation step. And then it's just a matter of plugging everything in to get my lower and upper bound. Now you'll notice here, I wrote out that confidence interval equation a little bit differently. I can substitute this formula in here and do it all at one time if I wanted to. I don't think that's probably optimal. It's easier to make mistakes. I just think it's a little bit easier if we break it down into parts. And you'll notice I have it written a little bit differently, which is, I've said before, mathematically, taking the square root of something that's squared is just itself. So another form of this equation will look something like this. But wouldn't worry too much about that in the sense that you can always do that intermediate calculation and make it a little bit easier. Okay. So let's do something now where we have a little bit more context. So let's say, well, actually, I want to make a point here before we go to the next example. No, I'll do that later. I think this one's worth spending more time on. So let's say the American Medical Association says that the average salary for physicians is $175,000. You feel like that's too high. You take a sample of 81 physicians and you find a sample mean salary of $160,000. You also calculate a variance from that sample and it's $324 million. Okay. And I'll blow this up here in a second, just jotting down what we were given. And we want to build a confidence interval that corresponds to an alpha of 0.05. So what level of confidence is my confidence interval going to be for if I use this alpha of 0.05? Yeah, so that's just the 95% confidence level. Now, one thing I could do real quick is rule out certain possible answers. I'm just going to write down the equation that we had for, and here I'm not going to do the intermediate calculation and show you what that would look like so we see both ways. So my confidence interval is centered around that sample mean. So if I look at these possible answers, if any of them don't have 160,000 exactly in the middle, I could rule that out right away. So let's say, one of them was 158,000 to 170,000. Well, 160,000 wouldn't be exactly in the middle there. I could rule out that confidence interval. I don't think there's any here that I can rule out because it looks like 160,000 is right in the middle of all these intervals. Right? So I wasn't very nice here. Right? You can't rule it out. But on the exam, I often will have one or sometimes two, where if you just look at them, the sample mean isn't exactly in the middle of that interval. That can't be the confidence interval. Okay. So from here, we just got to work out the rest of this. So I've got all the information I was given. I've got my confidence interval formula. This is on the formula sheet as well. So I could look at this and say, okay, I'm going to plug in what I know. So 160,000 is my sample mean. I don't know that t-value yet. My sample variance was 324 million. Hopefully I got right number of zeros there. And then my sample size was 81. And now remember, this represented the standard deviation of my sample means. So I could calculate this ahead of time and then just plug one value in there, maybe make my life a little bit easier. So the next step is going to be, I need to find that t-value. So the last piece that I need. So how many standard deviations above and below do I need to go to get alpha total in those tails or on each side of my interval? Well, if I've got two sides, there's going to be half of alpha on each side. My alpha was 0.05 over 2. So the area that I want in each one of these tails, 0.025. What's the other thing I need if I'm dealing with only having a sample variance and I'm dealing with that student t distribution? I need to know what my degrees of freedom is. Well, that was simply n minus 1. So I've got 81 as my sample size, minus 1. My degrees of freedom is 80 there. Okay. Any questions on kind of the setup? I guess, and this should start to, we're doing really the same thing. We've got 3 different types of problems. One, sample mean, where we know the population variance. The only difference there was, instead of using the sample variance, we used the population variance. And because we had that population variance, we could use the z values for the standard normal distribution. When we only have the sample variance, we have to use the student t. The third type of example we did last week was we were dealing with proportions. There, it's easy. We always get to use the standard normal distribution. Right? So the only time we use the student t is if we're looking at a sample mean and all we have is a sample variance. We don't know the population variance, which is the more realistic scenario. Okay. Any questions here before we go to that t table to look up that last piece of information? All right, so let's go to that T table. We wanted what? 0.025 was the area, and we got to scroll all the way down to degrees of freedom of 80. Oh, there we go. So 80, that T value that we need is 1.99, right? So that was the last thing that we needed. Now it's just a matter of getting this entered into our calculator, doing the actual computation, okay? So if I do that, all right, we identified everything we were given. We looked up that T value. If you did the intermediate calculation, your life would have been a lot easier because it works out to just be 2,000. So instead of having to put this in my calculator, I literally just have 2,000 there, right? And I can then compute my upper and lower bound relatively quickly. It's pretty simple, you know, this is a pretty simple equation once we get it down to this point. Okay. So I get this upper and lower bound of 156 to 164-ish thousand dollars, right? So if I'm just like plotting this on a number line, got what, 156K to 164K, just representing thousands there. So remember, the setup of this problem was that the American Medical Association said that the average salary, for physicians was 175,000. So if I build this confidence interval, I can turn around to the American Medical Association and say 175,000 cannot be the average salary for physicians based off the sample that I took, right? Because with 95% confidence, right, I can tell you that the true mean true mean salary for physicians is somewhere in this range, and 175,000 isn't one of those values. Right? So what we can do with confidence intervals is start to reject almost certain values for the true population mean, which this is going to lead us into and be very closely related to what we do with hypothesis testing. Hypothesis testing just allows us to say, not only can I reject this value, but I can tell you how strongly I can reject this value, okay? So yeah, this is how we'll kind of use those confidence intervals. I can, rule out certain values. You could also think about, I think the previous example, we had something like, I don't know, I think it was 0.84 to like 17 point something. Now that example didn't have any context, but let's say that we were measuring the change in something, like the average change, right? So we were thinking about the change in this variable was somewhere within this range. Why was this maybe an interesting confidence interval? I'm thinking about the change in something. All these values are positive. So another thing with confidence intervals, they become a little bit more interesting, or we can make interesting statements when they only include positive values. In other, different contexts, only include negative values. But if, they cross over, and I'm thinking about the change in something, well, maybe it went up, right? Maybe there was a positive change. Maybe it went down, right? It could be that there's a negative. So anytime I kind of cross, it also could be the change is 0. So anytime I cross over and have negative and positive values in my confidence interval, probably not a whole lot of interesting conclusions I can make there, right? So we can just start thinking about, once we've got the lower and upper bound, I think the visual is always nice. Just plot like in a number line and think about, this is where my true population mean is. What interesting statements can I make in the context of this example? And with the American Medical Association one, we could basically tell them they're wrong. Right? Any questions on that? Next thing we're going to do is see how we do this in Excel. Okay, so minimize this here. And I did all this last class, so I'm going to delete it all, because when you open this real estate class file that's under the in-class data folder on Canvas, you'll get something that looks like this, right? So you've got a bunch of different counties, some information about them. They're all in Indiana, and I have 3 different time periods, what the average home price was. So Zillow puts out like all this real estate data. It's actually really, if you like Google it, you could go and download it pretty quickly. You can get it for, I think the original one that I had that I didn't post because it was too big is every state, every county, every month for like the last 20 years, right? You can, I think they actually have an option. You can do it by zip code or something, which that's just a lot. So we're just going to deal with county level data in Indiana, right? I want to think about, what's been happening to home prices, okay? So I've got 3 different time periods. I'm going to start out, and I'm just going to think about, I've got 2015. Sometimes Excel does this annoying stuff where it formats something as a date. I just want to show the year. So I'm going to go up here to General. So I right-clicked, went to Format Cells. So you can just see I have a nice label, right? 2019 was the other year I had, and 2022. This is the January of every year. So things that we've already done that we can do pretty quickly is I can find my sample mean, I can find my sample size, and I can find my sample variance, right? So my sample mean, I'll just use the built-in average formula, right? That's how we've been finding our means. I'll select that 2015 variable, Control Shift, Command Shift on a Mac, hit the down arrow, selects the entire kind of variable for me. I'll hit enter, it'll close the parenthesis and send me back up to the top. Just kind of a nice little shortcut there. I can also do my sample size. And it's the same that we used last week. What do we use to find the sample size? There's a built-in formula. Yeah, I just want to count the number of observations. I'll use that count form or built-in count function. Select my variable, Control Shift, Command Shift on the Mac, hit the down arrow. And then the last thing I need, what's my sample variance? We've used this before, it's that var.s. Select that very first observation, Control Shift, Command Shift on the Mac, hit the down arrow, hit enter to close the parenthesis and send us back up to the top. Okay. This is stuff we've already done before, but you'll notice, if we're thinking about confidence intervals, I just found the sample mean, the sample variance, and the sample size. I've only need one more piece of information. I'm almost there already. Okay. So if I look at these, I'm using column J. That's the 2015 data. If I want to do this for 2019 and 2020, because I have this set up where the columns are right next to each other, when I copy this over one, it's going to update my cell references to be over one column. So 2019 would then be using the 2019 variable. In 2020, I go over 2 columns, so I'm using the 2022 variable. So that's exactly what I want. So I'll select these, go down here, when I have this black plus sign, drag them over so that it copies and updates that cell reference that's using the correct year. Also, I could probably figure it out, but I don't really care to or waste time. Just ignore these green things. Usually it's if there's an error in the function. I don't know why there's one here because it's working correctly and it's doing what we want. So I don't know why it's letting us know that. But so pretty quickly, we now have everything we would need to build confidence intervals for any one of these years about average or what the true average home price was. Yeah, so if I select these, if you go down here to the bottom right corner, see how it changes to like a black plus sign? If I left click and hold it and then just drag over, it'll copy it over. Like if I keep going, it'll, yeah, yep. So, right, we want to find a mean in Excel that's just using that average function and selecting whatever you want to find the average or the mean of. Be nice if it was just called the mean function, but I think Excel labels things the way that we talk in person to person. I usually don't say, oh, the mean of it, usually say average. So that's, I think, why they have it that way. Okay. Any other questions before we keep moving here? All right, so I'm going to leave a little bit of space because I'm going to break this down into steps in Excel. So we said this guy right here is the standard deviation of my, it represents the standard deviation of my, oh, I have it down here too. The standard deviation of my sample means. So I'm just going to go ahead and calculate this in a cell so I don't have to like put all of this in one. So I'm just going to break it up into parts. So here I want my standard deviation of my sample means. Okay. If you want to label this differently so you know what that means, I'm just shorthanding here SD for standard deviation. Okay. So the standard deviation of my sample means for each one of these years. Well, all that's going to be is the square root, which is that SQRT function in Excel. I'm then going to take the square root of my sample variance divided by my sample size. So my sample variance for 2015 divided by my sample size for 2015. Now, if I want to do this for the next 2 years, we'll notice it's just going to update to use the sample size and the sample variance for 2019. And then if I copy it over more, sample size, sample variance 2022. So because I've set this up in columns, I can just copy this over, and I've now got the standard deviation of my sample means for each one of these different time periods. And you can think about each one of these years, it's almost like you have a different sample. So eventually we could build a confidence interval for each one of these years, right? 3 different sample means. Okay. Any questions over that for the next step? Which is, I need to find these t-values. Right? So last week, we found the z-values for our kind of 3 benchmark levels, 90, 95, 99%. Those corresponded to alphas of 0.10, 0.05, and 0.01. Okay. So instead of z-values, because we only have sample variances now, we're going to have to find t-values. Okay. So how do we do that? Well, we're looking for that t-value that gives us alpha over 2 in each tail. Oh, sorry, I pointed to something that wasn't even there. We want the t-value that gives us alpha over 2 in each tail. Okay. So last week, when we were dealing with a standard normal distribution, we could use the norm.s.inv and just tell it that area 1 in the tail, which was alpha over 2. Well, I can't use norm.s anymore. I know I'm not supposed to be using the standard normal distribution, but I am still working in the inverse, right? I know the area in the tail, and I want to find the corresponding number of standard deviations. It's just now it's a t-value instead of a z-value. So instead of norm.s.inv, I'm going to be using the t.inv. That's all it changes. Norm.s becomes t. And I still tell it the area that I want in the tail. So alpha divided by 2, whoops, not 1, alpha divided by 2. However, with the t.inv, there's a second thing I need to tell it, which is, well, there's all kinds of student t-distributions. Which one, Excel says, which one do you want me to use? Well, we have to tell it that degrees of freedom, okay? We don't tell it the sample size. We actually have to tell it our degrees of freedom. That might seem stupid. Why can't I tell it the sample size? And they code it up so that it just subtracts 1. It's because we can use the student t-distribution for a lot of other types of examples where the degrees of freedom becomes more complicated. But for now, it's just my sample size, which is up here, minus 1. Okay. Now, if I copy this down, I know that my t-value is going to change depending on the confidence level that I want. So I want the alpha to keep updating when I copy this down, but I want to keep using the same sample size. I don't want that cell reference to change. In fact, if I don't do anything here, I'm going to get some errors. So I go up here. Okay, yeah, I want to freeze this sample size. So I just put some $signs around that cell reference. Okay. Now, I kind of already showed you this, but one of the issues is, it's a little bit frustrating, I guess, is that the built-in functions in Excel don't quite line up with what we're doing by hand because they only look at the left side of the distribution. When we look at that physical table, remember I said it's nice because we're always dealing with positive values. It looks at the right-hand side. The built-in function in Excel doesn't. It works just the same way norm.s.inv does. And it looks at that lower left tail or the cumulative probability. So if I tell it alpha over 2, it's always going to give me the negative number of standard deviations, or essentially what I need to get my lower bound. Well, the positive negative sign we're already going to have built into our formula. So we just want the absolute value. So we said last week we can just use ABS and then put parentheses around what we had before, and it should just drop that negative sign. Okay. Now, when I copy this down, it should get my 3 t-values that I need to build these confidence intervals. Okay. So the first thing I had was this t.inv. Alpha over 2 is the area I wanted to tail. I then told it my degrees of freedom, which was my sample size minus 1. When I copied this down, I wanted to make sure that sample size cell reference is frozen. And then I put the absolute value ABS function around the outside of it so that it just gives me the positive value. What's another way I could have done this? Do you remember from last week? Yeah. Yeah, I could have done, yep, instead of using the absolute value, I could have done 1 minus alpha over 2, and it would have given me the exact same thing because 1 minus alpha over 2 would have given me that positive t-value there. Okay. All right, so now we've got everything we need. It's just a matter of having Excel do this kind of simple calculation for us. Take the sample mean, add the t-value times that number of standard deviations, or sorry, times the standard deviation of my sample means. Okay. So here I'm going to do 2019 lower bound and 2019 upper bound. We're then going to do 2022 and then think about how we can think about what's happened to home prices pre and post COVID. I know we did something like this in Excel or homework 1, but this is a little bit more interesting. It has a lot more power. So my lower bound will simply be take that sample mean in 2019, right? I'm then going to subtract the number of standard deviations away I want to go. Well, if that's how many standard deviations away, what's the actual value, like number value I need to go? Well, 1.6 standard deviations times the actual standard deviations I have for the sample means from 2019. Okay. So took the sample mean, subtracted whatever the t-value was, times that standard deviation of my sample means, which I had already calculated ahead of time to make my life a little bit easier once I got to this point. Okay. Now, what I've got set up here is I'm going to build 3 different confidence intervals, but it's based off the same sample data. They're just 3 different levels of confidence. So I'm still going to base them all around the same sample mean, the same sample variance, and the same sample size. The only thing that changes is the number of standard deviations away I'm going to the left and the right, or that t-value. Okay. So I don't want the sample mean cell reference to change when I copy this down. I don't want anything in that standard deviation of my sample means to change. So I'm going to freeze that cell reference. The only thing I want to change when I'm trying to find the lower bound for the next 2 levels of confidence is this t-value. So that's the only thing I won't freeze there. Now, when I copy this down, I've got my 3 lower bounds relatively quickly. Okay. Any questions on that before we keep moving? So, oh, sorry, I missed you. Yeah.
Can you show me what the values are present again?
Oh, yeah. So we'll freeze that first one, which represents the sample mean. And then we'll freeze that last cell reference, which was the standard deviation where sample means, which had the sample variance and sample size. Yep. Yep. Any other questions? Move on here. So if I double click on that cell, it shows me the formula. I could type this out again for the upper bound and just use a positive, or kind of a nice little shortcut is if I go into that lower bound cell, highlight the function, or sorry, function, highlight the formula and copy it, and then go over here and paste it. Notice it gives me the exact same value because none of the cell references change if I copy and paste that way. It only updates cell references if I'm dragging it to copy it. Okay? So here, the only thing now I need to change from my upper bound is I'm adding my margin of error. Okay? So all I did was change the negative to a positive sign. Now when I copy this down, I've got my 3 upper bounds as well. Okay. Yep. So I just go into that lower bound cell, right click and hit copy. To get out of the cell real easy, just hit enter. Then I went over here. There was nothing here. I pasted it. The only difference in my upper lower bound equation is I'm adding that margin of error instead of subtracting it. So I changed that negative to a positive sign. And then from there, it was just copying that down by dragging that black plus sign. Okay. Any questions over anything that we just went through? You want to see a cell again or just, yeah. Left click. Yep. So if I don't even know what happens if I try to right click it. Let's see. It doesn't do anything. If I do try to do it when right clicking, looks like maybe I can right click as well. Yeah, then it just gives me more options if I right click. But all we're trying to do is copy. So just left clicking automatically defaults just copying. You can do, I mean, there's stuff that we aren't never going to use in this class. You can do different fill things where you jump by months instead of days and years instead of months. So, but for us, all we're ever going to do is just left click and use it to just copy so that it's updating the cell references. Any other questions before we keep moving here? That was a good question too. If I forget to say something, sometimes I forget about left, right click. Usually it's everything we're doing is left clicking, but occasionally, like when we wanted to change the format of the cell, right clicking is usually what gives us more options. Left clicking is always kind of default, like it doesn't show us any of these additional toolbars. All right, so I'm going to do this relatively quick for the sake of time. If you aren't able to follow along with this part, I'll be putting up the completed version of this after I get back to my office today. So you'll have this part of it to maybe copy over as well. It's really exactly what we just did. I'm just going to do it for 2022. I probably could have somehow done it here so I could set it up so that we could have it right next to each other and then copy and save over. But we've got everything we need. It should be relatively quick. We're going to use the same t-values because we've got the same sample size and we want the same 3 levels of confidence. So all I'm going to do is take my sample mean for 2022, subtract the t-value, multiply by that standard deviation of my sample means. And then from there, we said, when I copy this down, I don't want anything to change except for that t-value that I'm referencing. So I just did the exact same thing I did for 2019. I just did it for the 2022 sample as well. Okay. I can then copy this down, go in here, copy, paste that formula. I want the upper bound, so I change my negative to a positive sign. I just doing the exact same thing I did for 2019. Okay. So what's interesting about this is if I look at even at the 99% level here, right? So I've got a confidence interval for 2019 and a confidence interval for 2022 Indiana home prices. So let's look at this one. I'll round it a little bit here, but we've got 2019 goes from 124,000, so 124K, to about 147,000. So this was 2019. And then 2022 starts at 164,000 and goes to about 195. Okay. So all I did there, I took those two values and I plotted them so we have a kind of nice visual about what these confidence intervals look like. So here was 2022, here was 2019. So this is an interesting example because at the 99% level, what could I say here? Based off these confidence intervals, what's happened to home prices in Indiana? They've increased. So even worst case scenario, I shouldn't say worst case, but here, if the true mean in 2019 was the highest value in that range, right, that we said with 99% certainty, the true value is somewhere in this range. So even if it was the highest value, and even if the mean in 2022 was the lowest value in that confidence interval range, it would still be that 2022 is higher average home prices, right? There's no overlap in those confidence intervals. So anytime I have confidence intervals that don't overlap, I can make interesting statements, right? I start to actually have something valuable to say based off of the samples that I took. Now, I think if you do this for 2015 and 2019, it'd be very close. I haven't done it, but if you did it, I think it ends up looking something more like this, where there is a slight overlap if you go from 2015 to 2019. Right? I mean, because generally real estate home prices are generally increasing, right? But if you're looking at like a 3-year time period, it's really hard to see it play out as much. It's more like over a long period of time. And so if we looked at the 2015 to 2019, well here, because the confidence intervals overlap, I can't say anything because it could be that the true mean in 2015 was right here and the true mean in 2019 was down here, in which case home prices went down. Or it could be that the true mean in 2019 was here, the true mean in 2015 was here, which would say that home prices went up. Right? So just looking at confidence intervals that overlap, we can't really say much. The only time we can really make statements using the confidence intervals about whether or not something's smaller or larger than the other group or the other time period is if we don't have an overlap in those confidence intervals. Okay. Any questions on this before we kind of jump into hypothesis testing here to introduce that next topic? Okay. let's go to the slides here. So we worked through this. I've got some references for the Excel stuff that we did built in here. So the idea behind hypothesis testing, we're going to be really close to what you're doing with confidence intervals. I said earlier, once we have that confidence interval, we can rule out certain values for the population mean, just like we could tell the AMA they were wrong. So we don't know where this population mean, or we can do the same thing for proportions, but I'll probably say just the mean to keep it shorter. We don't know where this mean is, right? So we're going to develop what we call the null and alternative hypothesis. The null hypothesis is going to be, we're assuming that this mean is in some range or is a specific value, right? That will be our null hypothesis. The alternative hypothesis will just be the complement of that. So if I assume, for instance, that the average income in the US is less than 50,000, right? That's my null hypothesis. My alternative would be that it's greater than or equal to 50,000, right? They're complements of each other. Okay? So we're going to start out assuming something's true. Okay? This will be our null hypothesis. If we can find sample evidence that goes against that assumption, we'll reject it. So let's assume that, or let's assume that I assume. Let's say the null hypothesis is that I assume that the population mean for average income in the US is less than or equal to $50,000. That's what I'm assuming to be true. I then take a sample and I find 75,000. Well, that's pretty inconsistent with what I assumed, that it was less than or equal to 50. So I could probably reject the null in that case. But let's say I find evidence and it still goes against my null. So maybe I take a sample and I see the sample mean income is 52,000. Well, that's different than being less than 50,000. But if the true population mean was like, say, 49, it wouldn't be that unlikely or uncommon or improbable that I see 52 from my sample, right? Thinking about like the distribution around that population mean, it'd still be likely we see values really close to that. So even though I found evidence that went against my null, I might fail to reject it. Okay? So that's the idea. We have some assumption, we take a sample, using our sample statistic, can I reject that null hypothesis, what I assume to be true? Okay? So kind of one of the motivating examples I'll use here, and we'll really go deeper into this on Wednesday, is let's say that I look at domestic or mass market beers, and I think that they have an ABV less than 7%, right? This too hard a beer that I chose. So I think it's less than 7, right? That's what I want to try to test for, right? I take a sample and I find that it's actually 4.5. So the whole idea with my alternative hypothesis, that's what I want to test for. So is the ABV less than 7%? I'll assume the opposite is true and stack the deck against myself. So here, my null hypothesis, even though I think that the ABV is less than 7, I'll assume it's greater than or equal to 7%. I assume the opposite is true to stack the deck against myself. Okay. So I'll put this all up here and kind of talk a little bit more about this. So this null is going to be what we assume to be true, but our alternative is what we're trying to find, or what we think is probably the case. Okay? So for instance, if I think the average income in the US is less than $50,000, I'm actually going to assume it's greater than or equal to 50,000, right? And once we start working through more of the actual statistics of it, it'll kind of make sense why this stacks the deck against it, like we're stacking the deck against ourselves by doing this. But whatever we're trying to find, we assume the opposite is true, and that's our null hypothesis. And then the complement of that, right, the exact opposite would be our alternative. Okay. And we'll get more practice of this on Wednesday. So there's 3 different types of outcomes we could see, right? So we've got this null hypothesis. Maybe I assume the average income in the US is exactly equal to 50,000. So I take a sample and I find something very inconsistent with that null. Maybe I see 75,000 as my sample mean. That's very different than the assumed value of 50,000. I can reject the null, right? What I assume to be true based off my sample likely isn't, right? But maybe if I take a sample and I saw 52,000 as my sample mean, well, it's inconsistent with my null. Well, it's not that inconsistent, right? It could be that the true mean still is 50,000, even though I saw 52,000 from my sample mean. So it might not be inconsistent enough, right? Well, is 53,000 inconsistent enough? Is 54,000 inconsistent? Like, where do I draw that line? So based off what we know about the distribution of sample means, next class we'll figure out how we can draw that line. But for now, just know that it exists, right? There is some cutoff where anything past this point is sample evidence that's inconsistent enough with a null that we can reject it. And then the third one, the third kind of outcome, not very interesting. Let's say I assume the average income in the US is less than 50,000. If I take a sample and find 45,000, well, that supports my null. So of course I'm not going to reject it, right? I won't fail to reject the null there. So 3 different types of outcomes we can see with these tests. So I'm going to make the analogy, and hopefully you can kind of always return to this when if you get kind of confused with null and alternative hypothesis. So if the alternative is what we're trying to find, and the null is what we assume to be true by stacking the deck against ourselves. So let's think about a court case. What's the whole purpose of a court case? They think the person's guilty. Otherwise, I hope otherwise, why is the person there? Right? So they think you're guilty of something. That's what they want to try to find. So what would the null hypothesis be if I'm trying to find that someone's guilty? What should the courts be doing? They should assume that you're innocent, right? Like that, the court system is essentially hypothesis testing. Okay? So they want to find you guilty, but they assume the opposite is true. They make it harder for themselves to find you guilty, right? By assuming that you're innocent. So then the complement of that, the alternative hypothesis is that, well, that's what I was trying to find, the person's guilty. So I then go out, and if I can find enough evidence that goes against that null, so I assume that you're innocent, but then I find the murder weapon in your home, you don't have an alibi, and the person like did you wrong that ended up dead, right? You've got a motive. Well, all the evidence is pretty inconsistent with that you're innocent, right? So we reject the null, and that person goes to jail, right? Reject they're innocent. If we don't find enough evidence, or maybe we find evidence that you did, that goes, that supports the null, like you had an alibi, you don't have a motive, in fact, you actually like this person, right? The murder weapon's found in somebody else's home. Well, then you have evidence that supports the null that you are innocent, and you go free, right? So this court case analogy, like it's just a really, because I think it's something everyone can kind of relate to, or has some idea about how it should work, right? You can always kind of return to this when you're trying to identify null and alternative hypothesis. And then I think I have some quip about, OJ, if the glove doesn't fit, you must acquit, right? So we'll pick up on this hypothesis testing. We'll figure out how we can set that line for, is the sample evidence inconsistent enough with our null that we can reject it? And we'll do that on Wednesday, okay? All right. Enjoy the weather, and I'll see you guys on Wednesday.